All right, Math 3 students, welcome to the last lesson of Unit 7, our statistics unit. So, lesson 7.8, the topic is simulations. What a simulation is, it's a way to try to get at the answer without calculating directly. So sometimes things are just too complicated to calculate and possibly too expensive to try to go out and collect data for. So when that's the case, we can try to design a simulation to get at the answer. So go ahead and read the first question here. Okay, so your first thing they're asking is, do you have any concerns about how we conducted this? In other words, how we collected our data. And hopefully you see there's a problem. The problem is we asked the first 40 people that showed up. That is not representative data. And because of that, I really can't feel too good about the results of this. So I'm going to say the first 40 people is not a representative sample. Right? They might all have something in common, namely they walk to school more often or less often because the time of day that they're getting to school. Okay, but let's continue with our calculation, pretending that we have good data. So here we would need to get our z-score. Okay, we found 40% in our sample. 50% is the claim. All right, here's our n, and we got 16. So 16, that's where I got the 0.4. Okay. And the standard deviation, it's p times 1 minus p over the sample size n. So we work this out. We get a z-score of 1.26. Okay. Now, getting a p-value from 1.26. Okay, here's what our handy-dandy table tells us. Okay, and that's going to give me just over 10%. Now, do I leave this alone or should I double it? Well, let's look back at the question. Is there anything in the question that says we expect less than 50% of students to walk to school? I don't see anything in the question that says we expect less than 50%. So therefore, we're just testing, is 50% a good number? Which means we would be happy to take evidence that's really high or really low. So this is what we call a two-sided situation because we're happy to take evidence in either of two directions. So to get our actual p-value, we need to double this. So we get about 20, a little over 20% here. That is a large p-value, right? There's a good chance that this data was random chance, right? Almost 21%. So we do not have enough evidence. Running out of room. Not enough evidence to overturn the claim of 50%. Okay. But bear in mind, again, we know that this data is not representative data, so our calculation is not on firm footing. We're not sure if this really is a good conclusion because of the data. Okay, so continuing here, even though our study was flawed because of poor data collection method, we can still investigate what kind of sample proportions you would expect to see if the claim of 50% is true. Okay, now here's something that we're doing EDL, so it's kind of hard to do this as a class, but that was the goal, was to simulate this as a class. Okay, So as a class, we will use simulation to estimate a margin of error, which in turn will help us determine whether it is correct that the population proportion is truly 50%. We just need something that operates randomly with the same probability as the claim. Okay, so what can we come up with that has a random chance of 50%? So the obvious thing would be, hey, how about a coin, right? You flip a coin, two sides, 50-50 chance. So we might choose to use a coin to simulate a 50% claim. Okay, now the goal here was to have everyone in the class flip a coin $40 times and record the proportion of, it doesn't really matter. It doesn't really matter if you count heads or tails. Either one is fine. So I'll say, how about heads? Heads would represent the person walks to school. Tails, the person doesn't walk to school. Okay, now we typically have about 32 people in a class, so we would then have 32 samples or simulations that we could use to get at this question. Okay, so got myself a coin here, right? I'm gonna flip it. Just leaving the camera. Hey, I got heads, so I would mark that as heads, or in other words, the first person I asked walked to school, right? And I would continue doing this 40 times, right? And I'd keep track of how many heads I got. Then everyone else in the class would do the same thing, and we would add all of our data together to make a nice graph. Well, obviously, I'm the only one here. So I did this 32 times, right? And here's my results. Twice I got 14 heads. Once I got 15 heads, once I got 16, twice I got 17, 3 times I got 18, so on and so forth, right? So that's my actual data. I did it, flipped it 40 times, and then I did that 32 times. So each one of these tick marks represents 40 flips and how many heads I got out of the 40. So here it is as a decimal. So I'm now going to take that information and transfer it to my graph over here. Okay. So 0.35% heads, I got that twice. 0.375 once, 0.4 once, 0.425 twice, 0.45 3 times, and 47.5, I got that 5 times. 50% I got 4 times. Let's see, 52.5% 3 times. 55, I only got once. 57.5 3 times. 60% 4 times. 62.5 twice. And 65% once. Okay. So we're just kind of pretending that each one of these X's represents one of your results, even though I did it all for you. Feel free to flip a coin 40 times. Add an X to this. It'll be fun for you. Okay, so now let's go ahead and see what would happen if I try to figure out the margin of error here. Okay, so if we're doing a 95% confidence and we're trying to find our margin of error, that means we need to capture or catch about 95% of the data. So 95% of our 32 pieces of data is 30.4. So we want to capture 30.4 of the x's. So we'll have to round that off and say, let's try to capture about 30 of those x's. Okay. So now we want to draw vertical lines, and we want to exclude roughly one piece of data on either side. Well, the way it worked out for me, I can't really get only one on either side, right? Because I have two here, but that's okay. We're close enough. So we're going to draw a line right here, cutting it, and a line right here, cutting it. And now I've excluded 3 pieces of data instead of 2, but that's the way it works out when you do a simulation. You're not going to have exactly perfect every time. If I wanted more accuracy, get more data, right? What if I did this instead of 32 times, if I did it 1,000 times or 1,000,000 times, right? It's going to get more and more balanced on the two ends. But since I only did it 32 times, I didn't get a perfect balance yet. And you can see this really should be more normal, right? I kind of have this little dip here, which I really shouldn't get if I did it 1,000,000 times. And that's the thing about simulation. The more times you do it, the more accurate your simulation will be. But of course, every time you do it, we're all going to get different results. All right. So we drew our vertical lines. We caught roughly 95%, a little bit closer to 90%, but the best we could do. All right, now let's measure the distance between our lines. So our lower bound was at 0.35. Our upper bound was at 0.65. So the distance there is 0.30. The midpoint was at 0.5, which makes perfect sense because that's what our coin, where the midpoint of our coin should be, right? 50%. So what's the margin of error according to our simulation? According to our simulation, our margin of error is 0.15, right? Plus or minus. So we go to the 50 and we add or subtract 15%, and there we go. Now, for fun, see, normally what happens, we kind of went a little out of order. Normally what happens is we teach simulation first, and then we give you guys formulas, right? That's kind of the typical way. But you guys have the formulas already. So let's use our formula on this and see how it compares to our simulation. All right, so our actual margin of error, right? Z star times probability, probability times 1 minus probability over n. So for us, again, we're doing approximately 2 standard deviations. You can do 1.96 if you want. And for some reason, I wrote 0.4 there, 0.5. Working that out, we get approximately 0.158. So you could see, and if we had made this 1.6 instead of 2, we'd be even closer. So you can see our simulation result is pretty close to the actual result. And that's the goal of the simulation. And if we repeated more and more and more data collection, this number right here will get closer and closer to that value right there. And that's how simulations work. Okay, next page. So, as we've been discussing, a simulation is the use of a mathematical model to represent something, right? We're trying to recreate a certain scenario. And yes, it's important that we repeat it, because if we don't repeat it very often, then our simulation won't give us very accurate results. Okay. Now, we used a coin in our first simulation, so coins are great. Another thing you can use, dice. Cards can be good too, right? A deck of cards. Now, when you take AP Statistics, you'll learn about a random digit table. You can use one of those. You can use a calculator. A lot of calculators have the ability to do random integers for you. And of course, nowadays, probably the best tool is the use of a computer. Especially if you have some programming experience, you can write a program and say, computer, simulate this, 1,000,000 times, and it can do it in the blink of an eye, and now you have super accurate results. Okay, so let's try another problem. So you show up to Math 3, it's a pop quiz, 5 multiple choice questions, all have 4 answer choices. So N is 5, and we have 4 answer choices, okay? Your buddy Billy guessed on all the questions. And he thinks he was lucky today and got at least 4 questions right because he's just a lucky guesser. So the chances that he actually guesses one right, since there's 4 answer choices, is 1 out of 4, right? That's the actual probability of a correct guess. All right, so what we're going to do here is we're going to simulate this. Now what we want to do is see 5 questions, right? He guesses on all 5 and see how many he gets right. So how could I simulate this? Notice coins are 50-50, so that's probably not what I'm going to use. I could use a deck of cards, though. Right? How could I use a deck of cards? I know there's 4 suits in a deck of cards, right? So I would assign one of the suits as a correct answer. We'll say, how about hearts? Hearts would be correct. And all other suits would be incorrect. Okay, so that's one way to do it. So here I have a deck of cards. Make sure to shuffle it thoroughly and then randomly pick a card. Oh, Billy guessed wrong on the first try. Okay, then here's what's important. I have to put this back because if I don't put it back and reshuffle the cards, right, it's no longer a 1 in 4 chance. I got to keep that 1 in 4 chance throughout the entire simulation. So then I would put it back, mix them up again, right? Randomly pick. Question 2, no, that's a diamond. Billy missed question 2, so he's 0 for 2 at this point. Mix them up again. Hey, he got 1 right. 1 out of 3. For some reason, I keep getting queens. It's very rare. Okay, try again. Oh, got that one wrong. He's 1 out of 4. Okay. And do it one more time. Got that one wrong. So, turns out, Billy, on my simulation, first trial, he got 1 question right. He got 4 questions wrong, so he got 20% correct. All right, so now the goal would be each one of you to continue this 10 times. And then we would put all of our data together. So I already did this 10 times. I'll just go ahead and fill in what I got. Yeah, Billy started off pretty slow. Then he finally got a 60% on a quiz there on his 5th try. Back to a 0. Then a 40%, another 40%, and then a couple of 0%. Okay, so that's how it worked out for my simulation of Billy guessing on this quiz, and we did it 10 trials. So the goal here would be each and every one of you in the class do the same thing I just did, and then we would put all of our data together. But let's answer this. Based on our 10 trials, what would you say to Billy? Do you think he got an 80%? Was he likely to be that lucky? I'm going to say it was not likely, Billy. According to my simulations, the best you ever did was a 60%, and that only happened 1 out of 10 tries. So I would say it's not likely. It happened 0 out of 10. Okay. All right. Now, Billy, it turns out, he believes more in luck than he believes in my simulation. And he says, I only did 10 trials. That's too small. What if we did more trials? Maybe he would get more answers correct. So to speed this process up, here's what I did. I used my graphing calculator. And in my graphing calculator, there's a little button here, math. I go there, then I go to probability. Then I can ask my calculator for a random integer. And I said 1 to 4. And I want 5 such numbers. So the lowest number I'm asking my calculator to give is 1. The highest is 4. And give me 5 such numbers between 1 and 4. And then I called 1. Right? I called the number 1 is a correct answer. And then the numbers 2, 3, and 4, incorrect. So whenever you do your simulation, you have to make sure whatever method you're using, that your values, it's kind of hard to see that, isn't it? There we go, a little better. No, still not good. Too much light. There we go, shade it. You have to make sure the values that you assign match the chances of a correct or incorrect. So in this case, I had to have a 1 out of 4 chance. Okay, if I had said heads correct and tails incorrect, my simulation would be off the mark because that's not a 25% chance. So anyway, using my calculator, I do this and I go, hey, look, you got 1 right. And I do it again. Oh, 0 right. So this is how I did it much more quickly than actually using the deck of cards. And it turns out I did this 10 trials 32 times as if everyone in the class did it. And here are my results, my frequency table. So 75 times he got none of them right. 126 times he got 1 right. 86 times he got 2 right. 29 times he got 3 right. And 4 times he got 4 right, and he never got all 5 right. Okay, so I will go ahead and make a quick graph of this. Actually, I don't even want to make the graph. I don't have space for 75 x's. I'll just write the numbers in here. This is 75, 126, 86, 29, 4, and 0. So I just go ahead and make bars to match those. All right, so now based upon the class data, which of course I did all of it again, but we'll pretend, what is the likelihood that Billy got at least an 80% on the quiz? Well, 80% only happened 4 times out of 320 times. So you must have been awfully lucky because it's only going to happen by random chance a little over 1% of the time, according to my simulation. Now, if you wanted to do this, calculate it instead of simulate it, you might recall something you learned, I believe, in math too, combinations. I could get at this answer using combinations. So 5 answers or 5 questions, I want to choose 4 of them to be correct. The chance of getting it correct is 25%, and I need 4 of them to do that, and then I need 1 of them wrong. Or he would have been happy with 100% on the quiz. So 5 questions, I want all 5 of them correct. And if we work this out, we get approximately 1.56%. So my simulation yielded 1.25%. The exact value, if we calculate it out, is 1.56%. And that's the way simulations work. The more you do it, the closer this number will get to the actual value. Okay? And you guys may not even understand how to calculate the actual value here, and that's okay. That's why we taught you the simulation method. So just realize your simulation method won't be perfectly accurate, but it's going to give you a pretty good ballpark estimate of what the correct answer is. Okay. Moving on. Next problem. Let's say instead of our 4-answer choice quiz, Billy had a true-false quiz. Okay, how could you simulate a true-false quiz? Well, I would say by flipping a coin. Flip the coin, heads, correct, tails, incorrect. Okay, that's one method. I could say roll a die. And do, even number, correct, odd number, incorrect. Or I could do numbers 1, 2, and 3 correct, 4, 5, and 6 incorrect. I just have to make sure I'm matching a 50-50. Okay. Or I could use my calculator and do the same type of thing. So there's lots of ways to set up. Just make sure you choose a method that would match a 50-50 chance of guessing correct. Okay, moving on. Statistics is often used in court cases. So back in 1966, they were investigating discrimination in businesses. So you can read the scenario here. And in this case, we're wondering if there's gender discrimination taking place. So if I'm filling in this table as if there's no discrimination at all taking place, right, then half of the people promoted should be male, half female, and half of the people not promoted would be male and half female. Now, bad news here is these are odd numbers, so when I divide them by 2, I get a fraction, but that's okay. Right, so if no discrimination were taking place, those would be the exact numbers. But again, we can't get those exact numbers because we can't have a half a person. Okay, now question 2, this is kind of opinion-based. If there's obviously discrimination happening, what numbers would go in here? So I'm going to take it to the extreme. So I'm going to say, okay, all 24 males were recommended for promotion, none of them not. But realize there were 35 total recommended. So that means 11 females would have had to be recommended and 13 not. So that's as extreme as we could get, is saying this is discrimination. And now here's even more opinion-based. What's gray area? Like how many men versus women would have to be promoted to go, well, maybe it's discrimination, but maybe it's not. It could just be random chance. I'm really not sure. So you can go with your own numbers. For me, I'm thinking probably about 19 men versus 16 women. It's a little off balance, but probably not. It could be random chance. I'm just not quite sure. So filling in the table, there's my guess that maybe there's discrimination, but maybe not. Okay. All right, so now let's simulate this and see what happens. Now notice the difficulty here is that my probability of being promoted is 35 out of 48, which isn't a nice easy 50% or a nice 25%. It's kind of an unpleasant approximately 73%. So how do I set up a simulation with a 73% chance of success? Well, here's where those random numbers, random digit tables come into play. I can assign the numbers 00 through 72 as the person got promoted, and 73 through 99 as not promoted. Okay, you can see now there's 100 numbers here, right? 73 out of 100 promoted. That hits my 73%. And the remaining 27% would not be promoted. So that's how we do it in statistics if we have a number that's not so pleasant. Okay, so again, I would then pull out my calculator and I would say random digit, but this time I would start 0, 0 with the maximum of 99, and I need 24 such numbers. Okay, and then I would scroll through, and any number below 7 or 72 or less, I would say the male was promoted. So 1 promote, 1 not, another one promoted, another one promoted, another one not, and I would scroll through my list, keep track of how many of the 24 males were promoted, okay? And then I would do it a bunch, you would do it a bunch, we'd put all our numbers together, but we can't do that. So I just did it a bunch. And here is my data, okay? So 2 times I got 14 of the 24 males promoted. 3 times I got 15. 4 times I got 16. 5 times I got 17. 6 times 18. 5 times 19. 20 came up 5 times. And 21 came up twice. Okay, so there's my simulated values. Okay, now back to the historical example. It turns out in our discrimination case back in 1966, the number of males recommended for the promotion was 21 out of 24. So 21, they said give them the promotion, and 3 times they said don't give the male the promotion, which means for the females, it was 14 of them recommended for promotion, and 10 of them were not recommended for the promotion. So is this discrimination? Well, let's use statistics to answer that. So first question. You might recall from, I think, Math 2, you learned about independence. Okay, so testing this using conditional probability, we would say what's the probability that the person is offered or deemed to get promoted if they're male, right? Given a male. And does that equal the overall probability of getting a recommendation to promote? Well, promote given a male, 21 out of 24. 24. Overall promotion, 35 out of 48. Are those equivalent? Oh, I know I can get a common denominator here. So just double that. That's 42 out of 48. And I can see this is larger than that. Males are being promoted more frequently than they should be if gender is independent here. Okay, so these are not equivalent. Now, you could also, of course, look at it from the other row, the female row. So the probability promote given female, does that equal the overall probability of promote? And we already know it won't because it didn't over here, but I'm just pointing out you could have done it this way. So promote given female, 14 out of 24. Does that equal the overall of 35 out of 48? And of course, no. That is lower, right? Females were offered the promotion at a lower rate than they should be if it were independent, if gender had no impact. But there's one thing we need to remember. Our actual breakdown, it's impossible for these to be exactly equal because this is an odd number, so it won't divide evenly by 2. So it actually, this calculation cannot be independent. Because we had an odd number here and we had 2 categories, so Running out of room. So an odd number with two categories, there was no way we could hit it fairly and break it exactly in half. Because humans, we can't have a half of a human. All right, but anyway, we can see that these aren't even close. So continuing. There's another way to test for independence, right? The multiplication property. So the probability of promotes and male, does that equal the probability of promote multiplied by the probability of male, right? If these are equal, then we have independence. Well, we know they're not going to be equal. We just tested it the other way, but just to refresh your memory, probability of promoting intersect male. That's 21 successes. And over here, let's see, probability of promote is 35 out of 48, 24 out of 48, and promote and male, so out of 48 there. So the question is, are those equivalent? And working this out, we find out, getting a common denominator again, 42 out of 96 on the left, and on the right I get 35 out of 96. They're not equal. Again, being a male is increasing your chances of being offered the promotion. But we can do the same thing for the female. So promote intersect female. Does that equal probability of promote multiplied by probability of female? So let's see, promote and female, that's 14. And promote 35 out of 48. And female 24 out of 48. Getting common denominators, so this is 28 out of 96, and the right side again, 35 out of 96, and we can see they're not equal. Again, being a female is lowering your chances, which we already knew. We were going to fail both of these because we failed up here. As soon as you fail one, you'll fail all of them. But I just wanted to show you all four to kind of refresh your memory. Okay, so final question. Looking at your simulation, what do we think? Do we think, oh, I guess I forgot to do the confidence interval back here. Whoops, let's jump back to number 4, our confidence interval. So let's see, this is 32 x's again, so 0.95 times 32. Right, I want to capture approximately 30. Turns out I have 2 on each end, so right, I got to do that. I can only get 28, but that's okay. So my confidence interval here would be 17.5, and we're going to say 3.5. Okay, so there's my confidence interval. Working that out is 14 to 21, right? Notice 21 hits right on the edge of that confidence interval, so it's really dicey. But let's go ahead and calculate, because again, we went out of order. We know how to actually do this with a z-score. So I'm going to do that. My z-score, 21 out of 24 males were offered the promotion. The overall promotion rate, though, was 35 out of 48. Standard deviation should be based on the overall. Okay, work that z-score out. We get 2.27. Pulling out my handy dandy table, 2.27, that's quite a ways, right? So getting my p-value, Now, assuming we went into this thinking that the discrimination favored males, which in 1966, I would assume that would be our hypothesis, we would leave this as a one-sided, and that would be my p-value right there. If I went into this having no idea that males were favored back in 1966, then I would say, oh, two-sided and double this. But even doubling it, we still have a low p-value. So there is evidence of discrimination taking place. And again, remember, the lower that number is, the stronger your evidence is, right? We're saying that this would happen due to random chance about 1% of the time. So I'm going to say it's probably not random chance here. There's probably actual discrimination happening. And that's the way that these significance tests or testing a claim, that's how they work. All right, ladies and gentlemen, that's all for the lesson. I hope you enjoyed the statistics unit. If you did, remember, AP Statistics can be in your future. And good luck on your Unit 7 review quiz and your Unit 7 exam.